Okay, good afternoon. Our speaker today is Matteo Tagliazucchi, who is a PhD student at the University of Bologna working under the supervision of Michele Moresco, and who also graduated here in a cosmological thesis studying the CMB, and today is going to tell us something connecting CMB distortion and possibly Pulsar Timing Array data. Please.
So, thank you. Matteo, I'm a first-year PhD student here at the University of Bologna. I work with Michele Moresco and Nicola Borghi in the field of gravitational wave cosmology. But now, today I will talk about this work that I carried out in collaboration with Matteo Braglia, Fabio Finelli, and Mauro Pieroni, that uses the methodology developed during my master thesis, updated in consideration of the recent detection of PTA experiments. So, to introduce this talk, let me briefly say that one of the goals of modern cosmology is to measure the primordial power spectrum of curvature perturbation generated during inflation. Such quantity is very important because it would allow us to better understand inflation and the formation of large-scale structure of our universe. The most stringent constraints to this quantity comes mainly from CMB anisotropies data, in particular the one of the Planck mission, that reveal a near-scale invariant, slightly red-tilted PPS, shown in that equation here, with the amplitude and the spectral tilt tightly constrained by Planck. However, these constraints are valid only at this scale here, plotted in green, that goes from 10 to the minus 3 up to 10 to the minus 1 per megaparsec. Whereas galaxy surveys can extend this constraint up to 1 megaparsec, smaller scale plotted here remains largely unconstrained. In this sense, the recent observation of stochastic gravitational wave background made by PTA could suggest an enhancement of the PPS by roughly 8 orders of magnitude with respect to Planck values at the scale where PTA is sensitive, that goes from 10 to the 6 up 10 to the 8 per megaparsec. And dotted here with small black dot. Such enhancement of the PPS would inevitably induce spectral distortion of the cosmic microwave background, that are tiny departure from the perfect black body shape of the CMB spectrum. Indeed, as we will see in a while, spectral distortion is sensitive to the PPS in the range of scale that is between CMB scales and PTA scales, that goes from 1 per megaparsec up to 10 to the 4, 10 to the 5 per megaparsec. And so the goals of this work are to quantitatively study the implication of this hint of enhancement of the PPS and PTA that lies in PTA data on CMB spectral distortion and CMB anisotropies, and to see and to quantitatively explore the synergy between these three probes to constrain the PPS over this wide range of scales. So, since this work is focused on CMB spectral distortion, let me discuss what they are and how they are generated and why a PPS leaves an imprint on them. As we all know, the CMB has a spectrum which has a black body shape with a temperature measured in the early 90s by the COBE FIRAS mission, and plotted here with the black line. Spectral distortion are tiny departure from this shape. How are they generated? They are generated by non-thermalized energy releases in the early universe. To understand the mechanism, consider a box that represents our universe with a hole filled with electrons and photons in thermal equilibrium. If we look inside the hole, statistical mechanics tells us that the spectrum of photon is the one of a black body. Now, if we heat up one side of the box, that this mechanism could correspond to some energy release in the early universe, the photons that collide at the hot side of the box have an increasing energy. And so the shape of their spectrum is not the one of a black body, but has that green curve there. Now we consider the interaction between the electrons and the photon inside the box. In particular, the Compton scattering is able to redistribute this energy. When we heat up photons, they get that red line as a spectrum. Then the quantum scattering is able to redistribute the energy, and so to transform the spectrum of photons in that green curve, which is not yet a black body because it has too many high energy photons, which however can be transformed into low energy one by considering number changing processes like the double Compton or the Bragg-Straubing. When these three processes are efficient, all energy releases are thermalized, and the black body shape is restored. In particular, the resulting spectrum will have an increased temperature with respect to the original one, and it's plotted here in blue. When this occurs, we say that there is a G distortion, G-type spectral distortion, even if it's not properly a distortion, because it has still the black body shape. When are spectral distortions generated? When we consider the universe expanding, so if we let the box expand, the free path between electrons and photons increases, and so these processes are not anymore efficient. And when this occurs, they are not able to fully thermalize energy released in the universe. The non-thermalized energy creates spectral distortion. We distinguish mainly two kinds of spectral distortion, and plus the G, which are mu and Y, depending on which processes become inefficient. Now that we understand what spectral distortion are, we can plot the total intensity, we can write the total intensity spectrum as the sum of the monopole black body term, plotted here as detected by FIRAS, plus the distortion term. The distortion term is the sum of the three different types of spectral distortion. Each spectral distortion has its own shape G, Y, and M, and its amplitude small g, small y, and mu. And the shape of spectral distortion are plotted here in this bottom right panel compared to the black body curve. And only notice that here I plot the spectral distortion for very large value of spectral distortion amplitude, roughly 20, while the COBE FIRAS emission set a very tight constraint on these two parameters. The spectral distortion amplitude are computed knowing the rate of the energy injected in primordial plasma through this integral here, where J, this function J, describes how much the energy contribute to either mu or Y at each Z. There are several ways to compute such functions, several approximations. We use the one implemented in the Einstein-Boltzmann solver class, and the result is this one here. As you can see, all the energy injected before 10 to the 6 redshift, as only the blue curve is equal to 1, all the other is 0. Blue curve is the one for G distortion, and so for Z greater than 10 to the 6, 2 times 10 to the 6, all energy releases is thermalized because our processes are efficient. As the universe expands, the processes becomes less efficient, and so mu distortion are created. Look at the green curve at 10 to the 6 always. At 10 to the 5, Y distortion starts to be created, and in the late universe, only Y distortion can be created. Why the PPS creates spectral distortion? So the presence of density fluctuation in the primordial plasma causes some regions of that plasma to be hotter and denser than others. All these regions can be treated as a black body at different temperature. And when photons diffuses from overdense to underdense regions and vice versa, there is a mixing of black bodies at different temperature that result in a black body with average temperature plus some distortion term. So the initial energy does not go all in the average black body, but there is some residual that creates spectral distortion. So on one hand, we have an isotropization of the CMB pattern at small scale, known as the damping, and on the other hand, we have spectral distortion. Particularly, the energy rate due to such dissipation of acoustic wave is given by this equation here. If we plug this expression in the previous one for the spectral distortion amplitude, we can rearrange something and get a simpler expression for mu and Y generated by the PPS. The important thing here are W mu and WY, called window function, and tell how much the PPS contribute to mu and Y at each K. In particular, we see here in blue the Y function, Y window function, that has support for Ks that goes from 1 to roughly 10 to the 2, while the mu window function has support for k that goes from 10 to 10 to the 4. These correspond to the range of scale that I plotted in the second or third slide. And so this is the range of scale where spectral distortion can test the PPS. We are almost there. Let me just discuss the imprint of PPS and the other observable. CMB anisotropies depends on the PPS through this integral here. But now, maybe the most interesting part is why an enhancement of the PPS could explain the detection of nanograph. When we have large fluctuation in the inflaton field, we could not use first order perturbation theory, and at second order, scalar and tensor model coupled. In this sense, density fluctuation can induce tensor modes, which are primordial gravitational wave. Such primordial gravitational wave permeates the universe and form a stochastic and contribute to form the stochastic gravitational wave background. We call in particular this contribution scalar-induced gravitational wave background, and the energy density of such SGWB is given by this double convolution integral, where we clearly see the dependence on the PPS. Now, this summer, PTA experiment claimed the detection of the stochastic gravitational wave background and studied the possibility that this stochastic gravitational wave background was due to scalar-induced gravitational wave. And they found that the scalar-induced gravitational wave hypothesis is favored over other models from a Bayesian perspective. So we remind now the goals of this work, which are quantitatively study the implication of the scalar-induced gravitational wave background on spectral distortion, and to quantitatively explore the synergy between the three probes developed so far to constrain the PPS. How was the analysis? So we took a template, the lognormal distribution, which is able to mimic the shape of bumps in the PPS. This template in particular is able to describe the amplitude, A, the width, delta, and the location of the bump, K star. And we perform an MCMC analysis using MontePython and class to constrain the template parameters. We use different data sets, namely Planck plus FIRAS, Planck plus PIXIE, which is a future proposed spectrometer with better sensitivity than FIRAS, and plus Planck plus PIXIE plus nanograph data, which we took as a representative PTA experiment. We use the likelihood implemented in MontePython, in particular the FIRAS and the PIXIE-1 are mock, and so to avoid combining real and simulated data, we use a mock likelihood also for Planck. And when we had nanograph data, we basically took the MCMC samples generated by the nanograph collaboration for this particular model, the lognormal template. We compute the marginalized posterior, and we include it in our as a prior in our analysis. Since the likelihood are mock, we have to pick up fiducial, and we consider three cases. The best one are the parameters that best fit nanograph data, but these parameters gives a signal of mu and y, which is the same of the one generated by the near scale invariant PPS measured by Planck. In the case 2, we took a fiducial inside the nanograph 1 sigma contour, but that generates a high level of mu above the plane sensitivity of PIXIE, which is roughly 3 times 10 to the minus 8, 2 or 3 times 10 to the minus 8, but still a y that cannot be detected by PIXIE. And finally, in the case 3, we took a PPS, which has a large bump inside the spectral distortion window, and that generate a mu and y that are very loud for PIXIE, but allowed, very loud for PIXIE, but allowed for FIRAS, because they do not break FIRAS constraint. These are the 3 PPS that I just described. The red one is the best fit of nanograph. Sorry, the blue one is the best fit of nanograph. The red one is this case 2, and the black one is the case 3. Of course, in the case 3, the detection of PTA could not be due to such PPS, but to other things like supermassive black holes or other new physics signals. These are the predicted spectral distortion in solid mu and in dotted y for each cases. In particular, notice that the black PPS, the case 3, generates both mu and y above the Farad sensitivity, well above the PIXIE sensitivity, that is the yellow line in the right. So basically, these are the results. Let me explain what they are. In the above panel, we have the 3 triangle plots, one for each cases. And in each triangle plot, we have the contour coming from the various dataset. And in the bottom panel, we have the reconstructed PPS. So basically, it is the distribution, the posterior on the PPS computed starting from the samples. To understand this plot, let me say that white regions are those not allowed by data. And so we can see that in all 3 cases, FIRAS plus Planck, blue contours, do not see the enhancement in the PPS, dotted here with black line, but are able to set an upper limit on the amplitude of the PPS of roughly 10 to the minus 4 in the range of scale of spectral distortion, while smaller scale are completely constrained. And the presence of Planck is able to set a lower limit on the location of the bump, and this is because a bump at too large scale would affect CMB anisotropies. And this is true for all of the cases. Let's go to Planck plus PIXIE, which are their orange contour. In the first case, Planck plus PIXIE is still not able to reconstruct the PPS, but it's able to improve FIRAS constraint of roughly 4 or 5 orders of magnitude. While in the case 2, we have something very interesting. Even if mu is above the planned sensitivity of PIXIE, we only have a hint of detection of the PPS. See the light region there. But the near scale invariant case is not excluded. This is mainly due to 2 causes. The first is that we are marginalizing over astrophysical program for spectral distortion, which of course degrade the sensitivity of PIXIE, and therefore in the orange case, as you may see from the above triangle plot, the detected mu at 3 sigma is still consistent with the near scale invariant value. And second, even if we remove foreground, red colors, we are not able to reconstruct the PPS. I do not plot here because it will be roughly the same of the orange curve. You can see the red contour that are perfectly overlapped with the orange one. And this is because even if we detect mu well, and in absence of foreground, we detect it very, very well, we are not able to break the degeneracy between the parameters, and so to fully reconstruct the PPS. When we instead detect both mu and y, like in case 3, Planck plus PIXIE is able to reconstruct well the PPS and to exclude the near scale invariant case. So this is the main result about Planck plus PIXIE, but now let's look at the synergy between CMB and PTA, which is maybe the most interesting part. In the first case, the synergy is, let me say, marginal, because as you can see from the above triangle plot, we have the green contour that are only with nanograph, and the purple one, nanograph plus CMB, where CMB I mean Planck plus PIXIE. As we can see, PIXIE is able to cut off some regions of the parameter space allowed by nanograph, because such regions produce a too high spectral distortion signal. In case 2, this synergy is very, very strong. Since there is a high level of spectral distortion, CMB plus PTA are able to well reconstruct the PPS very, very well, in all the range of scale, because basically adding nanograph to PIXIE is able to break the degeneracy of the parameter. And notice that this is very interesting because the PPS is reconstructed very well, even if we do not detect a 3 sigma mu. And this is very, very, very interesting. This result can be shown in a different way also with this, which is the reconstruction of the energy density of the gravitational wave background. In case 1 and case 2, green contours are the same for the two cases because are nanograph samples, nothing, they are nanograph samples. Purple contour are CMB plus nanograph in the two different cases. Again, in the first cases, adding CMB to nanograph is able to cut the tail of the omega GW because that tail produces again too much spectral distortion. And in the second case, the improvement on the reconstruction of omega GW is incredible because there is a lot of parameter space that becomes not allowed when we add CMB. In particular, notice the red curve, the red space there. That is the LISA sensitivity range. And so we see from this plot that adding CMB to PTA could have very interesting implication in interpreting the results, the data coming from future space-based experiments like LISA. This is the summary of the result. Let me conclude by saying that, of course, this analysis can be improved by changing the template, choosing a template that can take into account more features in the PPS, can be expanded with a discussion on primordial black holes formation and overproduction, and can be improved by including other spectral distortion observables like the T-mu correlation or spectral distortion isotropies. In the end, I think that this work has some very interesting result that can be summarized as follows. A PIXIE-like experiment can really bridge the experimental gap between anisotropies and PTA, and the synergy between PTA and CMB and spectral distortion, can be help in constraining the PPS over a wide range of scale and have important implication for interpreting future gravitational wave data from space-based mission. And notice that somewhat these results are conservative because we used a future spectrometer like PIXIE, but there are proposals for more advanced experiments like the one described in the Voyage 2050. That's all. Thank you so much.
Okay, questions from the room? Carlo first.
So since you're treating data from different experiments and using quantified, so you need to be aware of all the systematics of the experiments, but also you should be able to build a set consistent covariance matrix of the various experiments in combining data. And so since you're looking at very low signal, so are you consistently accounting for the covariance matrix of all the experiments together, or you're treating them independently?
We are treating them independently. In the sense, PTA and CMB are different. Well, we do not use the likelihood of PTA. We take their posterior and we use it as a prior. So we do not have the full likelihood of PTA data. Some sort of bias theory. For anisotropies plus spectral distortion, we treat the likelihood as independent, so we can sum the logarithm of the likelihood. And for the covariance matrix that we used, we basically used the Monty Python recipe, which is start the run when the software is able to compute the covariance matrix. It will compute it for you and use it in the next run. So we do not build a real covariance matrix for the two experiments, for the two experiments plus the prior coming.
Can you remind us what PTA constraints are in terms of constraint on PPS and how nanograph is going to improve this constraint?
Okay, so I have some backup slide, maybe this one. it's not super clear, sorry. The gray violin plot are basically nanograph data. They fit mainly the first 4 or 5 pulsar, because these correspond to pulsar, I think. And they fit this signal with different models, new physics signal, or the standard supermassive black hole one. So, sorry, what was the question? How nanograph can improve this?
What are the constraints from PTA and how nanograph is going to
The constraint from PTA on the PPS for this template.
actual constraint on the gravitational wave background. Even more basic question.
This one maybe. This one is the only constraint that you can have on the gravitational wave spectrum at this frequency. So we have some points in the space. Each point, I think, corresponds to a pulsar that they follow. And how to improve, just increase the time of observation, I think.
There's no matter of statistics, having more pulsar.
Yeah, statistics can be included when we combine nanograph data with other pulsar timing array experiment. There are several international collaboration for PTA, international PTA, European PTA, and so on. There are some Chinese experiment on PTA. So maybe when you will combine the data coming from all experiment, because each experiment do not follow the same pulsar, maybe you can have more points and so have more statistics, and yeah.
I have a couple of questions. One, I know nothing about this PIXIE. Where is it supposed to fly?
It is not supposed to fly.
It is not.
Unfortunately, no. But there are several other.
So why was it?
Let's say this is a PIXIE-like experiment. A spectrometer with sensitivity on mu of 2 × 10⁻⁸. Okay. It's a forecast, of course, and can be applied to all.
Not planned yet.
Not yet, not officially. No, there are some proposals with this sensitivity here. You see in blue FIRAS sensitivity, and this is a forecast for a future spectrometer, PIXIE-like. I should have been maybe more clear with that sensitivity. Notice that there are other proposals of more sensitive experiment that's a better sensitivity. Yeah.
And if you can expand a little bit on your second point in the conclusion, the one about the overproduction of supermassive, I didn't understand exactly what.
Yeah. So the standard mechanism to generate primordial black holes is the one that made by an enhancement of the PPS. So the standard mechanism to produce black holes is to have a bump in the PPS like this one. So actually the red and the blue curve could produce primordial black holes, of course. Here I do not plot the mass, but basis, depending on the frequencies on which the bump occurs, primordial black holes will have their own mass. And so maybe the value of the PPS could be so high to overproduce primordial black holes. We have constraint on the presence of primordial black holes because they cannot be the totality of dark matter in some range of mass scales. And so it needs to be accounted the overproduction of primordial black holes in deriving constraint. But it's not easy because the formation mechanism of primordial black holes depends on mass assumption. There are a lot of assumptions in compute the production of primordial black holes given a bump in the PPS. And so the result can be completely different depending if you are considering non-Gaussianities or other assumption. Yeah.
But this bump that you are supposed to consider the power spectrum, does it manifest also in the abundance of high redshift systems and high redshift cables? Did you check if this consistency that you have there on the bump that you're assuming, does it manifest consistently also with the abundance of
sincerely not because yeah, I do not know almost anything about tables.
just to follow, you said that the mass, the more that the code depends. Can you give an idea of the mass?
I do not remember. I have to check some other plot that I have. If you wait, I can check. No, I don't remember. If you on that scale, for example. Sorry. Oh. Dov'è? This is my master thesis. Yeah. Yeah, sorry. I gave you the result. On that scale, from 10 to the minus 5 up to 10 to the minus 8 solar masses. On that scale of PTA, yeah.
Okay. If there are no other questions, not even from the remote audience, no. Okay, thanks again.
Che come si passa e poi la fanno